Hey guys, welcome to our little solutions video for the practice moving forces. So we'll go ahead and get started with number one, where a sudden gust of wind catches the sails of a sailboat, causing it to increase its speed. So we're going to want to draw our force diagram. We're going to have the boat being pulled down by a force due to gravity. We're going to have an equal and opposite force, the normal force of the water, acting against it to keep it afloat. So now we have the wind suddenly catches the sails. So the wind catches the sails, and we'll call that F of W for force of the wind. So that's going to catch the sails and cause it to increase its speed. And when it's increasing its speed, it's accelerating. And unbalanced forces cause acceleration. So we know that the force of the wind has to be greater than the force, and I'll call it H2O, right? That force of the water. So how does the force on the boat due to the wind compare to the force on the boat due to the water? The force of the wind has to be greater than the force of the water because there's an acceleration. The boat is changing its speed. Number two, a man is being pulled behind a ski boat at a constant speed. What is the net force acting on the skier? So he's being pulled behind a ski boat at a constant speed. Again, right, keeping this guy afloat. He's got his force due to gravity. And we've got that normal force of the water. So now, pulling him forward, keeping him heading towards the boat there, we have the tension in the rope. And then pulling back on him, we can call that the force of the water. We can call that the friction of the water. Something to do with the water counteracting the tension in the string. And so now it's asking about net force. In order for an object to remain at a constant velocity, the net force is going to equal 0. And what that means is that the forces are balanced. So that means that, that is, right there, that the normal force equals that force due to gravity, and that the tension equals the water. So net force is 0 because if we subtract these two forces, so if we take that normal force minus our force due to gravity, they're the same, so we get 0. Same with the tension and the water. So next, move on to number 3. So the first stone in an exciting curling match slowly slides to a stop after it's released by the curler. What causes the force to stop? So let's draw our diagram here. So we've got our curling stone. Now we can draw our forces on it. So this is on a sheet of ice. And now we have the force due to gravity of the stone, and we have the normal force of the ice. If it'll let me draw it. So we have the normal force of the ice. And now, so the curler slides the stone and then releases it. So once it's released, the applied force is no longer there. That is not carried with the stone anymore. And because it's slowly sliding to a stop, we know that there's a force of friction caused by the ice on the stone. And so then what force, if any, causes the stone to move after it is released? What is keeping that object moving is that it already had some velocity before. So once it was released, it had a velocity, and that hand is off. So once the hand is off, that applied force, that push, no longer stays with the object. Number 4, a skydiver has just jumped out of an airplane and is hurtling towards the ground. So is this person accelerating? So let's draw our force diagrams here. So he just jumps out. So if he is just jumping, his velocity or her velocity will be changing as the skydiver is falling downwards. So their velocity, as they're moving down, so that force due to gravity will have to be greater than the air resistance. FAR, we'll call air resistance. This person is accelerating because their forces are not balanced. The force due to gravity is greater than the air resistance that is trying to keep that person from falling. So now after a couple minutes, the skydiver has reached maximum, the terminal velocity. So when they've reached max velocity, that means that the person is no longer accelerating. They're just traveling at a constant speed. So that traveling at a constant speed, now we have our force due to gravity. And here it says, how does the force of gravity compare to wind resistance? So now we'll call that air resistance is the wind resistance, right? It's all means the same thing. So now force due to gravity is equal to the wind resistance, that air resistance, and so now he's moving at a constant rate. So then number 6, skydiver pulls the ripcord and feels a sudden jerk upward. He's still moving very fast. The skydiver, what direction is the skydiver accelerating at? So let's draw our force diagram first. We still have that force due to gravity, right, pulling down on our skydiver, but now he pulls the ripcord and the parachute opens up and he feels a jerk upward. So that upward jerk, right, we're going to call that is going to be, we'll call F of P, and that is the force of the parachute. It's still going to be, right, your wind resistance going through the parachute, and so that sudden jerk upward causes the skydiver to begin to change his velocity. Now he's still moving downward, but his velocity has just changed, that he's traveling at a lower velocity, which means that the acceleration has actually pulled the skydiver upward. So then number 7, near the end of the exciting jump, slowly drifts to a constant speed. So if he's at a constant speed, now that means that the force of the wind in the parachute then has to be the same force as the force due to gravity. Because now they're constant, or they're balanced, he's traveling at a constant speed. So how does the upward force due to the air pushing on the parachute compare to the downward for that of gravity? It is equal, and we know that because he's at a constant speed. So how does the force of the air on the parachute and skydiver compare to problem 5? It's the same. It is the same. So that is your practice for moving forces.